today's session. So today we are going to talk about DRAMs. What are DRAMs? What is a DRAM cell?
Single MOSFET with a capacitor.
Why is it called a DRAM? Why is it called dynamic RAM, not static RAM?
It involves charging and discharging of capacitors.
So even in a static RAM, the internal nodes are also capacitors. There's parasitic capacitance there. They get charged and discharged.
But
That
we
is
need
how you
to,
store a 1 and a 0.
we need to refresh them here. We cannot leave them.
So in the DRAM, the way the capacitance charging and discharging happens, refresh is a mandatory requirement. It is not required at all in SRAMs. So you definitely need to have a clock which would come at a regular frequency so that your DRAM contents are refreshed. SRAM doesn't need a clock. आप उसको 10 साल तक कोई क्लॉक ना दो, वो अपने डेटा को होल्ड करके रख लेगा. DRAM can't say that. DRAM में refresh के लिए you have to give a clock every now and then. Is that okay? Now, as already mentioned by one of you, DRAM is denser. It has one transistor and one capacitor instead of 6 transistors in the SRAM. So how does the DRAM cell look like? This is how a DRAM cell is. If you want to write into this cell, what do? You take bit line to the desired level, turn the word line on, and this node will get charged or discharged to the desired level. Now, this C should be small and this M1 should be big. Why?
Charge faster.
Charge?
Faster.
To charge faster, so that the internal node can get charged up very fast. And do you realize that when I turn the word line on, there is actually charge sharing that is happening between BL and INT? Because
Yes,
in
sir.
reality, BL is also a capacitor. है ना? So if this C is very large, then what happens? Let us say this is CBL, and let us say this C storage. It's very large. What happens? The charge sharing would happen, and instead of almost VDD being stored at INT, I will end up storing VDD minus say delta V. And this delta V would be large. Are you able to see this? When this C storage is small, then the voltage at INT will be VDD minus delta V, small delta V, where this delta V is smaller. Are you able to appreciate this point?
Yes, sir.
Okay.
We are talking with respect to the bitline capacitance, like with respect to bitline capacitance, C should be small.
Yeah. So with respect to bitline capacitance, C should be small means जितना small होगा उतना अच्छा है ना?
अच्छा, yes sir, yes.
So as small as possible. But there is an opposing constraint also. That opposing constraint is that the B should also be large. But if we come to that, let us first look at how the read operation happens. To do the read operation, the word line would turn on and this capacitor would share charge onto the bit line. And then the sense amplifier turns on and both INT and bit line are discharged. Are you able to see this? So where would the bit line pre-charge be over here?
So can you please repeat this part?
So what part did you understand and what did you not understand? I will then repeat accordingly.
So we were talking about the like the reading, but I got disconnected.
Okay. So when you want to read this particular cell, what do? You turn the word line on.
Yes, sir.
What happens? At once CBL and C store get connected.
Yes, sir. Yes, sir.
Again, charge sharing happens.
Yes, sir.
And you sense which direction the charge sharing is in, and determine if C stored a 0 or a 1 through the sense amplifier.
Yes,
And the
sir.
sense amplifier now discharges both bit line and INT, or charges both bit line and INT.
So sense amplifiers, why is it charging bit line or INT? Like why we are talking about the sense amplifier charging bit line or INT?
Yeah, because it arises from my question that I was asking after this.
Okay.
At what voltage will you precharge the bit line?
Okay.
What voltage will you precharge the bit line? Suppose you want to read a 0. What should be the voltage?
Sir, we can either precharge the bit line to VDD or VDD by 2, but VDD by 2 will be even more prominent.
Precharging the bit line to VDD by 2 is more promising, because then what happens is that when you are charge sharing VDD from the internal node, then you know that bit line will rise. And when you are charge sharing 0 from the internal node, then you know bit line will fall. So they are moving in two different directions. And you can utilize that to your advantage. Precharging it to full VDD, what can happen is that even if INT has gone to some voltage because of charge leakage or whatever, bit line may end up discharging a bit. And that can be a problem for you. You might end up reading that as a 0 instead of a 1. समझ में आया? नहीं. Hello?
So ये वाला पॉइंट नहीं है.
So आपने bit line को suppose VDD पे pre-charge करके रखा, and then you do a read operation. The internal node had already, due to leakage or whatever, had reached a level of VDD minus 200 millivolts.
Yes, sir.
So in reality, because it was storing a 1, I would not expect my bit line to fall anything. Bit line should remain stable, but because internal node was 200 millivolts lower, bit line falls a bit. Charge sharing would happen.
Charge sharing.
On another node, you had stored a 0. So in that case, the bit line would have naturally fallen much higher. So now the difference between 0 and 1 appears to be like this. Pretty close to VDD, but this has to be considered as 1 and this has to be considered as 0.
Yes,
On the
sir.
other hand, if you were precharging to VDD by 2, then even if internal node has discharged a bit, your bit line would rise. And in case when the 0 was stored, the bit line would fall. This is the distance between the two of them. Okay, and you will see that this margin could be higher. Is that okay?
So can we say pre-charging the bit line to VDD by 2 is much beneficial because the margin is greater?
Yes.
Yes, sir. Yes.
Now comes the third thing, which is called refresh. Which means that, see, this internal node would leak over time. Where would it leak? There is a junction capacitance of this MOSFET. There is subthreshold current going through this MOSFET. So many things are happening. So this internal capacitance would leak, int node would leak. And what you want is that to restore the cell content, suppose it has leaked by 200 millivolts. If you do a read operation right there and then what happens? This will still be read as VDD, and I will restore VDD value onto int node. So this is called as dummy read. This is not a user triggered read. This read happens anyways, so that the contents of the DRAM are maintained. This is the refresh part. And to increase the duration between these dummy reads. So do you realize that when the dummy read is happening, actual read cannot happen? So your DRAM is unavailable for use. The customer or the user is waiting until your dummy read closes. Only then a real read can be initiated again. So you want to increase the spacing between dummy reads because that reduces the unavailability of your DRAM. For this, you need to reduce the leakage of INT node. To reduce the leakage of INT node, there are two ways. First, keep M1 to be very small. Second, if you cannot keep M1 to be very small, or even if you are able to keep M1 to be small, keep C to be as big as possible. So that even if some charge leaks out, the dip in the voltage level is not very significant. Instead of 200 millivolts, only 100 millivolt dip is coming. So now you can double the duration or double the interval between two refresh cycles. So while in the first slide, earlier slide, we had said that M1 should be big and C should be small. That was what we had said there. Over here, we are talking about exactly the opposite thing. Are you able to see this?
Sir, why should we increase the storing capacitor C?
Because if, let us say, I leak is the current that is leaking. If the capacitor is large, then it will take extra time for the voltage on this int node to fall. So restoring the value of int node will be easier. See, the threshold is int node should not fall below 200 millivolts or 300 millivolts. So the duration it would take for int node to fall for the same leakage current will be higher if the capacitance is larger.
Okay.
So you can increase this interval then.
Okay.
So these are contradictory requirements on the capacitance sizing and the M1 sizing. Are you able to see this?
Sir, but increasing the capacitor will increase the access time, sir.
It will increase the access time. Why do you say so?
Because
if the capacitor is large, it will charge the BDD by 2 of bit line higher, much higher or much lower. So capacitor large means that it will actually help your read operation also.
Sir, it will be able to store large charge. I accept that. But the RC constant will increase more. Ultimately, the time required to read will increase.
Oh, okay. So see, you finally would have the sense amplifier driving the bit line and the internal node. Only one internal node is going to be visible to the sense amplifier. This capacitance is 100 femtofarad, let us say. This capacitance is 5 femtofarad. So 100 ki jagah 101, it appears as 105 femtofarads. Not a very big deal, no?
Suppose if we want to say that to reduce the leakage, we are increasing the capacitor which is storing the contents. So then it will go. It can increase only by 2 magnitudes.
So you do not reduce leakage by increasing the size of C. Be careful. You just increase the interval between refresh. Leakage here you can reduce only by reducing M1. By changing the size of C, by using a larger C, you are just increasing this interval between 2 refresh cycles.
Okay.
है ना? Leakage को तो कोई impact नहीं आएगा. Leakage will not change because you used a larger C. In fact, leakage would only increase because the higher a higher VDS will remain for a longer duration of time.
Okay.
So leakage will probably only increase, but you increase the interval at which you will do the read operation, dummy read there.
Okay, sir.
So we are calling this dummy read, like the refresh as dummy read, right?
Yes.
Okay. Okay. Sir.
We're calling it as dummy read because no one asked us to read it. This is just being done.
Yes, sir.
Yes, sir. The other node of sense amplifier remains, the reference bit line remains as VDD by 2 only, right?
So the sense amplifier, what does the sense amplifier do? It will amplify the difference between bit line and bit line bar to full VDD and ground, is it not?
Yes, sir.
So the bit line would go to full VDD if that was what was required, or it will go to full ground if that was what was required. As bit line goes to ground, the internal node will also discharge, or as it goes to ground, the internal node would charge up. Is that clear?
Sir, how we will generate actually VDD by 2, sir? Because real supply is a
We will
VDD.
come to that. So we आगे जब मत करो, जहां तक बताया वहां तक is it clear?
नहीं सर, और रिफ्रेश में सर जो रीड बोल रहे हैं, तो रीड तो सिंपली रीड कर लिया, रिफ्रेश समझ में नहीं आया, रिफ्रेश में हो क्या रहा है?
Refresh is also simply read.
रीड
We're
तो
just
हो
calling
गया,
it
but
dummy read because it is not triggered by the user. It is simply read. Row by row, you read every row. What happens? All the cells get refreshed. All the cells are written back into.
sir, it is a power wasting field, sir.
Yes, DRAMs consume much more power than SRAMs. But
And
they are
sir,
much denser. But they are much denser. आगे बोलो.
रिफ्रेश का मतलब क्लियर नहीं हो पा रहा है, कर क्या रहा है? रीड तो ठीक है, रिफ्रेश रीड सेम है आपने बोला, बट क्यों ऐसा हो रहा है?
So what do you understand by the term refresh when we talk of DRAMs? What do you understand? I'm not saying that your understanding may be correct or not correct. What do you understand as of now?
रिफ्रेश सुन के मेरे को यही लगता है सर, सम वोल्टेज वी हैव टू रिगेन करना होता है, उस वोल्टेज पे दोबारा चले जाओ, काइंड ऑफ थिंग.
So you want to replenish the charge onto the internal node.
Okay.
Whether it was a 0 or a 1, you want to bring it back to the original level. Am I right?
Yeah, ताकि हमारा डेटा लॉस ना हो.
ताकि data loss now.
Yes.
So during read operation, what happens?
Internal node discharge होगा according to bit line voltage.
Internal node would share charge with the bit line.
Yeah, share
It
charge.
may get charged up or it may remain low.
Yes, sir.
So what happens?
Either internal node will decrease by some voltage delta V, or it will be a very less voltage.
It will either decrease by some voltage or it will increase by some voltage.
Yeah.
I know. And then you activate the sense amplifier. What happens? Bit line goes to 0, and as a consequence, even INT goes to 0.
Bit line goes to 0, INT. Yes, sir. Yes, sir. Going to 0. Yes, sir.
So you were reading a 0. When you initially connected the bit line and the internal node also rose to VDD by 2 minus delta. Because of charge sharing. Because of charge sharing.
Yeah.
Now when you activate the sense amplifier, bit line goes to 0 and simultaneously INT also goes to 0. So whatever loss of charge had happened, you replenish that charge.
Okay. Yes, sir.
Okay? And that is why it is called refresh. You refresh that charge.
Okay. So every read will do this kind of mechanism.
So this is how read happens.
Okay, sir.
But for refresh, even if a read operation is not triggered by the user, you will do dummy reads. Every row you will access once every 1 millisecond.
And okay. Yes. Got it.
Okay, na? Anything else?
Sir, how does
Okay, you go first.
Yes, Malika.
sir, how does increasing the size of the capacitor lead to increase in the dummy read duration?
Interval,
Yeah,
not duration.
interval. Yeah, interval.
So you tell me, sense amplifier has a offset dependent on voltage, that I want
Yes.
my the voltage to be at least this much there so that I can sense a 0 or a 1.
Yes, sir.
So, and we are saying capacitor will leak charge through M1.
Hmm.
So voltage is Q is equal to CV.
Mm-hmm.
So Q by C is the voltage. If you increase the charge that you can store on the capacitor,
Hmm.
then even if the same current is leaking, the delta V would be lesser because
Yes.
the capacitance is larger.
Mm-hmm.
So sense amp required a particular delta V. Now that delta V is lesser in the same duration, so you can actually let it discharge for some more time
Okay.
and then do the refresh.
Mm-hmm.
So that is how a large capacitor helps in increasing the interval between two refresh cycles.
Okay, sir.
ठीक है ना?
Mm-hmm.
Anything else?
So I understood why we are refreshing, but can you please explain how we are refreshing the internal load?
We simply read. We simply read every row.
Okay.
So when you read a row, what happens? अभी हमने बात करी.
So charging or discharging.
Sense amplifier will fully charge or fully discharge the internal node. So any
Yes.
loss of charge which would have happened because of leakage is taken care of.
Okay. Okay.
ठीक है ना?
सर जस्ट फॉर क्लैरिफिकेशन, जो इंट नोड है सर उसका स्विंग अपन 0 से VDD ले रहे हैं, वोल्टेज स्विंग से.
आप बताओ. Good question. Very good question.
क्योंकि सर
What do we have there? Bitline को int node से क्या चीज connect कर रही है? Is it a transmission gate or a NMOS?
डायरेक्ट ट्रांसमिशन गेट तो नहीं बोलेंगे ना सर.
Pass gate है ना ये तो.
यस सर.
This is pass transistor logic.
यस सर, पास ट्रांजिस्टर. या
So what is happening here? What would be the?
Sir,
Can I transfer a VDD to int node like this?
No, sir.
गेटेड सर. मतलब सर अगर बिटलाइन को VDD/2 पे ले लिए और रीड ऑपरेशन सर अगर कर रहे हैं तो 0 इंट पे अगर है तो चार्ज हो जाएगा. समथिंग नॉट क्लियर कि क्या हो रहा है सर. इंट नोड रेंज क्या हो रहा है वोल्टेज.
नहीं. If you just try to work it out, what did we say? That I have my bit line at VDD/2. Let's go to the read wala slide again. I had my bit line at VDD/2. When the internal node got connected, I discharged a bit, and then sense amplifier ensured bit line went to 0. And as bit line went to 0, because this is on, this also goes to 0. This is simple.
Yes sir.
Now, if int node stored 1, what would happen? Bit line would rise. Then
Yes,
once the sense amplifier turns on, it will take it to 1. Now this 1 on the bit line needs to transfer to int node. How would you do it?
So WL high करके.
WL हाई रहेगा.
WL high रहेगा. Word line high है, लेकिन ये तो NMOS है.
Yes sir.
तो NMOS कितने?
There will be a VT drop.
So VDD minus VT जाएगा.
Yes, there will be a VT drop. Now, if you do not want a VT drop, what do you need to do?
So pass gate.
Pass gate तो लगा ही हुआ है ना अभी.
Sir, charge the capacitor.
How? That you anyways are doing, na? You anyways are charging the capacitor from the bit line You are sending charge through M1 to INT node.
Transmission gate. Sorry, I said pass gate. Transmission gate.
Oh, so then it's kind of double the area.
Yes, sir.
Can you do something else? Think of assist schemes that we used in SRAMs. Can you do something like that over here? What did the assist schemes do?
Sir, can we have WL at VDD plus VTH?
Yes, so we can overdrive the word line. If we overdrive the word line, what happens?
Sir,
Yes, sir. Then VDD will.
VTH drop will be compensated.
Yes, the drop gets compensated. ठीक है? Is the refresh operation clear now? If you take word line to a level which is higher than VDD, I can compensate for the VT drop that could happen because of the pass gate. Therefore, DRAMs would have some charge pump that would raise the level of word line to a value which is higher than regular word line. Okay. Any questions? Okay. So if this is clear, that is memory, the DRAM cell operation is clear, then we look at in terms of refresh overhead. See, we said that refresh needs to happen at a regular interval. So because leakage goes exponentially with temperature, the refresh rate can actually go very high at high temperatures. Okay. What is happening? That you count through all the row addresses once per refresh interval. And in that duration, the memory cell contents are refreshed. What this means is that in that duration, when you are kind of reading these, doing dummy read on the memory array, in that duration, you cannot do another operation. Because read is happening, you cannot now do any other read or write on the DRAM. So the DRAM is unavailable during the refresh period. Are you with me? Are you able to see this?
Yes, sir.
And this also gives a brief quick calculation of that. If the if there is a 8192 cross 8192 array and every excess is 10 nanoseconds, so how much total time is given there, is lost in refresh? So that overhead is also being calculated. Is that okay? Any questions?
Sir, what is this 10 nanoseconds, sir, exactly? Read time for SRAM cell or like we need
We're
a
not talking about
like base
SRAMs
for,
now, no? We're talking about DRAMs.
no, we need a base for comparison, no, sir, between those both, so that we can say which one is better. So what is
Sorry?
this 10 nanoseconds?
No,
We need a base to compare SRAM and DRAM, right? So
no. When I'm storing data in a DRAM, who's talking about SRAMs?
okay, so this is only for DRAM then. So what is this 10 nanoseconds, sir, exactly?
What do you understand by read time?
I mean, without the refresh, only I'm like only regarding the read time.
What is read time according to you?
So I mean, sir, the read operation should be completed. I'm like from the starting from the word line to the end where we read the capacitor value. So
Yes.
I think that should be the read time.
Yes, exactly. That is what it is.
So we don't have the refresh time in this.
Is refresh
included
time
in that.
different from read time? What did we just say? Refresh
Okay.
is equal to dummy read.
Yes, sir. But yes, sorry. Yes, sir,
Read
but
time is the refresh time. per
P
row.
row.
Per row. So you need to see how many rows are we talking about. How many rows are we talking about? 8192 rows in this example. So 8192 times into 10 nanoseconds upon at what interval? It's at 3 milliseconds interval. So 3 into 10 raised to the minus 3 into 10 raised to the 3. And finally we get the percentage overhead. Fine.